Welcome student. Now today we are going to know about the spectrum of a black body radiation. What exactly is the we say that spectrum? Spectrum means a color, means corresponding wavelength regarding the radiation. Let us consider we have the black body and it is maintained at a different temperatures. Let us consider a body of any size, any shape, and temperature it is given to this body. And at a different temperature, if we observe the color emitted or a spectrum emitted by the black body at a different temperature is drawn in the form of curve. Let us see, here it is a black body. Here I am going to write, this is your black body, and corresponding to that one, if it is maintained at a different temperature, it will start radiating, and this radiation corresponding to the different wavelengths. Okay, and seems to be considering this is the spectrum, that is the different wavelength that we need to draw in the form of curve, which is drawn in between intensity versus wavelength. This nature of the graphical representation carefully should be drawn while explaining everything. This is the intensity on y-axis. Corresponding to this x-axis, we have the wavelength, and we need to observe both intensity corresponding wavelengths. Wavelength means a spectrum, different colors. Okay, here it is. Initially I am going to maintain this black body at a particular temperature in the range. Initially starts from this 1000 Kelvin. So why it is taken 1000? Simple to remember. Starting from this 1000, then I am going to increase this by 1250 Kelvin, and then again rises to 1450 Kelvin, and then again 1650 Kelvin. Okay, now within this temperature range we are going to variate the different curves at different temperatures. What happened to the intensity versus wavelength means I am going to maintain this black body at initially 1000, then I am going to observe a one curve. How it behaves, let us see. At 1000, curve that I am going to draw is just like this. Here the corresponding wavelength increases, intensity of the curve increases, and certainly it goes on decreasing. This is the nature. This is the peak point where I am going to get the maximum corresponding wavelength at a maximum intensity. So corresponding this maximum intensity is a I max 1. I max 1. Corresponding this is lambda max 1. For the first curve, initially the intensity gradually increases and then later on decreases. This is the observation. Let us write the observation one by one. What happened as the temperature varies, or curve observation is as follows. In case of curve only, firstly we need to observe the curves, not of the curve, it is curves, different curves. This is corresponding to the 1000 Kelvin. So what happened as the temperature again increases means, let us observe at 1000 initially as the corresponding intensity here increases as the temperature rises slowly up to 1000, and later on it reaches to the maximum and later on it will decreases. Means corresponding wavelength, if we increase, initially there is a rise in the intensity up to certain level, corresponding maximum wavelength we are obtaining at a maximum intensity, and later on gradually it goes on decreasing. What happened to this 1250? Let us observe the curve carefully, because while drawing we need to carefully draw this diagram or the curves. Gradually it goes on increasing, and it start to be ununiform now. Here it is non-uniform curve, and here the corresponding this value is a maximum. This is, we say that I maximum 2, and corresponding maximum level of this is lambda m2. So this value is less as compared to this one. So we need to draw one conclusion later on the basis of that one. See, this curve is a uniform curve, but as the temperature increases, curve should be ununiform. Let us get this by increasing the temperature. What happens? As the temperature increases, the maximum intensity level goes on increasing gradually. See, for the third curve, see the curve. Okay, this is the curve. This is non-uniform curve. This is second curve corresponding to 1250 Kelvin, and this curve is regarding 1450 Kelvin. See, observe this one. This is a corresponding maximum wavelength corresponding to this one. This is a I maximum 2. So the value, again the maximum value corresponding to this one is lambda m3, but again it is slightly lesser than the lambda max 2. On the basis of that one, we need to draw conclusion at last. So we need to draw one more curve regarding the 1650 degree Kelvin or Kelvin. Here it is. Corresponding cursor gradually increases, and then uniformly it goes on decreasing. See, this is corresponding 1650 Kelvin, and corresponding wavelength again it goes on decreasing, corresponding to lambda m4, and corresponding intensity it is maximum, that is lambda maximum 3. These are the different curves. Now let us write the observation. Curves between intensity and wavelength. Intensity and wavelength increases, and then after corresponding maximum intensity start decreasing. This is the first, we say, conclusion. Second, the curves are ununiform as temperature increases. And third one, now corresponding to that one, if we observe the first peak, first curve, this is the area under the curve. What it indicates? Area under the curve. Area under the curve indicates amount of radiation radiated or emitted per unit area per unit time for black body. This is all about, we say, conclusion regarding the curves. What about the temperature? Regarding the temperature, we have the different conclusions. As temperature increases, curves are non-uniform. And corresponding to that one, what happens as the temperature increases? Curves are uniform, non-uniform. Here the uniform curve, non-uniform. If you observe, starting from the first to last, see, if we draw the line regarding this, what happens? The maximum wavelength corresponding to the maximum intensities, what happened? Lambda max is a maximum 1, maximum 2, maximum 3, maximum 4 for the corresponding intensities at different levels. As we say that temperature, if we observe the temperature corresponding to the first curve, we have 1000. Corresponding to the second, we have 1250, and for the third one 1450, for the fourth one 1650. If we observe the temperature for the maximum, it is 1000. Then for the 1000 it is maximum. As the temperature increases, temperature increases, here it is, increases, temperature increases, corresponding wavelength decreases. This is the conclusion that we need to draw while studying all that. And if we observe the wavelengths, they are non-uniform. Peak is shifting towards the left. See, maximum wavelength, it is shifting towards the left. Means curves, as the temperature increases, peak or maximum wavelength shift towards left. See how it is shifting towards left, not towards the right. It is shifting. Here it is again left. Instead of this one, if it is just like this, it is shifting towards right, but it is shifting towards each and every curve. Starting from the initial point, the peaks are shifting towards left. These are the, we say that this is the spectrum or observation regarding the intensity versus wavelength at different temperatures, that is 1000, 1250, 1450 and 1650 Kelvin, and curves obtained are like this. First curve is a uniform and likely to be, others are start to be ununiform as the temperature increases. These are the observations regarding the curves. These are the observations regarding the temperature. Here already we saw the spectrum of a black body radiation. On the basis of that one, a certain conclusion that we are going to draw, and that conclusion has been given by the scientist, that is Wien's displacement law. Depends upon the displacement corresponding to the different curves which are shown here. In these curves, the displacement is towards the left. So depends upon that one. The Wien has given one conclusion, that is maximum wavelength corresponding to each curve is inversely proportional to absolute temperature. And if we are going to observe the lambda maximum into T is equal to, so as to discard this constant of proportionality, we will have to take some constant that is known as B, that is constant known as Wien's constant. This is a Wien's constant. Wien's constant. And this Wien's constant has a value that is 2.898 into 10 raised to power minus 3 meter Kelvin. Here I am specially going to write here meter Kelvin. This is the unit corresponding to this one. So this is about the Wien's displacement law. Later on, we have the emissive power. Emissive power. See observation. Now area under the curve indicates certain thing, that is amount of energy, emissive power denoted by the symbol E, amount of energy radiated, that is Q, per unit area per unit time is known as emissive power of a body, whereas Q is the amount of radiation. Amount of radiation emitted. Radiation emitted. And what about this A? Area. T? Temperature. Temperature. So this is all about, we say that, emissive power. Now corresponding to this emissive power, we have coefficient. Coefficient. As we know, coefficient is a ratio of similar quantity. Coefficient of emission denoted by the symbol that is small e, and this is a ratio of emissive, this coefficient of emission E is equal to emissive power of a body to the emissive power of a black body. What it means? Emissive power of a general body to the emissive power of a black body. This ratio corresponding to that one we can term is as a coefficient of emission. Now depends upon that E, we are going to draw certain conclusion that if E is equal to 1, this body is a black body. Which body? Black body. If E is equal to 0, it is perfectly reflector body. Perfectly a reflector. It reflects total amount of energy which falls on the surface of it, and black body which absorbs total amount of radiant energy which is falls on the surface of it. What about the ordinary body then? We have this E is, if it is less than 1, then it is a ordinary body. Ordinary. This is the conclusion while solving the numerical problem. If E value it is equal to 1, then we are going to write the conclusion that body is a black body. If E is equal to 0, that time we say that it is a perfectly a reflector body. And if E is less than 1, then that body is a ordinary body. Thank you.